So yesterday I discussed about the necessary conditions for determining the stability of any system. So I told you yesterday that there are two conditions which needs to be satisfied, and these two conditions are called as necessary conditions. So without these necessary conditions, we cannot conclude further whether the system is going to be stable or not. So it's very important for any system to be stable that the first two necessary conditions are satisfied. So after finding whether the system is the system satisfies the two necessary conditions, then comes the sufficient condition, which is also necessary in order for any system to be concluded as stable or unstable. For example, if we look at this particular characteristic equation, so this is the equation that represents a system, and it is designed to conclude whether the system is stable or not. So if you look at the necessary conditions, the two conditions says that all the coefficients of the given characteristic equation should have same sign. So the first condition is satisfied. All the coefficients associated with this particular equation have same sign. For example, the coefficient with s cube is 1, with s square is also 1, and with s is 5 and 125. They are all positive, and thus the first necessary condition is satisfied. The second necessary condition states that no coefficient associated with the equation should be missing, and thus if we look at this equation, we see that no coefficient is missing. So both the necessary conditions are satisfied. And now if we look at this, if we try to locate the roots of this particular equation on S plane, so since this is a simple equation, it's a third order equation, and we can easily evaluate the roots which are which represents the roots of the characteristic equation. And one important thing that I forgot yesterday to tell you, that we generally apply Routh Hurwitz criteria as sufficient condition for systems where we cannot easily evaluate or locate the roots of the system. So this is something that will be discussed in the next slide. So if we factorize this equation, what we get is the following simplified equation. And if we look at the roots of this equation, so what we get is the first root as s1, which is minus 5. The second root is 2 plus j 4.5. The third root is 2 minus j 4.5. So these are the three roots that we obtain from the given equation. And since we see that this particular equation satisfies the two necessary conditions, but still it have two roots that lie on right half of S plane. So if you try to locate these roots on S plane, what we observe is that S1 lies on left side of the S plane, left half of the S plane, while S2 and S3 are lying on the right half of S plane. And any root, as I told you before, that any root of the system that lies on right half of S plane is sufficient to make the system unstable. And thus, because of the presence of roots on right half of S plane, S2 and S3, the system will be unstable. Now, this is why we are required to apply the sufficient condition as well in order to finally conclude whether the system is stable or not. So first thing, and I again repeat that whenever you're given the characteristic equation of any system, the first thing that you will be checking is the two necessary conditions, because if any of the two necessary conditions is violated, in that case you straightforward will have to write the system to be unstable. But if in case the necessary conditions are satisfied, both the necessary conditions are satisfied, then we move forward towards the application of sufficient condition, which is Routh Hurwitz criteria. So although the coefficients of the third order equation are positive, the equation still has roots with positive real part, which makes the system unstable. So this particular example is the example of an unstable system. Hence, for determining stability of higher order system, in addition to the necessary conditions, a sufficient condition is further needed, which is called the Routh Hurwitz criteria. So this is what we now simplify things into, that whenever you are required to find the stability, or you are required to conclude the stability of the system, so you will first check out whether the system characteristic equation satisfies the first two necessary conditions. When the first two necessary conditions are not satisfied, or any one of them is not satisfied, you will straightforward conclude that the system is unstable. In case both the conditions are satisfied, then you'll move forward towards applying Routh Hurwitz criteria to the equations. So now we start discussing what is Routh Hurwitz criteria. Consider the characteristic equation which was also taken previously. So from this characteristic equation, so we are taking a general form of characteristic equation having the order n. Now, in case of Routh Hurwitz criteria, what we do is we have simple 2 or 3 steps that will be applied. So step 1 says that you will have to rewrite the polynomial, or ensure that the polynomial is written in descending power of s, and then you will have to construct the Routh table by arranging the coefficients of the equation as follows. Now first, before constructing this particular table, you will have to ensure that the characteristic equation is given in the form of descending power of s, because if it's not given in the descending power of s, then you'll have to rearrange it and write it in descending power of s. After writing it in descending power of s, you will be populating the Routh table. So this particular table is termed as Routh array or Routh table. In fact, this is table, and the coefficients after filling inside the table, you call that thing as array. So you have the highest power of s as n. So you start with s to the power n. The subsequent term that follows is s to the power n minus 1, s to the power n minus 2, n minus 3, up till s to the power 0. So you will be writing the terms corresponding to s starting from the highest power to s to the power 0 on the leftmost column of this table. And on the right side, you will be assigning or writing coefficients from the equation that you observe here. So if you look at this particular equation, you have coefficients associated with it as a0, a1, a2 up till an. So you'll be using these coefficients populating the first two rows in this manner. So the first element corresponding to the row of s to the power n comes from a0. So this is a0. So you are going to put this value a0 here. Then you will be putting the value a1 in the second row, first column, followed by a2 in the first row, second column. Then you have a3 in the second row, second column, and so on up till an. So this is how you are going to populate the first two rows using the characteristic equation. And after populating this, so it's simple to it's easy to remember that how you are going to locate the roots, how you're going to populate or write the roots. So you'll first have to write a0, followed by a1 below it, then you have a2 after a0, then a3 below it, then you have a4, a5, a6, a7, and so on. So you're going to write the two rows in this manner. And after writing the two rows, what you now do is you will have to evaluate the third and fourth row. So you will be evaluating coefficients b1, b2, b3, and c1, c2, c3. And this is done by using the previous two rows. So the first two rows are formed from the given polynomial, while the other rows are constructed by using elements of previous two rows, which means that if you talk about the third row, you will be constructing this particular row using the previous two rows. So how do we evaluate b1? So there is a simple formula which was given by Routh, and that is b1 is equal to a1 multiplied by a2. So this is in this manner. You start with a1, multiply this by a2, minus a0 multiplied by a3 divided by a1. So this is how you write the coefficient b1. So it's a1, I repeat, a1 multiplied by a2 minus a0 multiplied by a3 divided by a1. Likewise, if you want to evaluate b2, so for b2 you will be using this again, coefficient a1 again. You will be multiplying a1 with a4 minus a0 into a5 divided by a1. So it's written here, a1 into a4 minus a0 into a5 divided by a1. So this is how you evaluate b2. And similarly, you are going to evaluate further coefficients following b1, b2. and so on. Likewise, for evaluating C1, what you do is you will be using the previous two rows corresponding to s to the power n minus 1 and s to the power n minus 2, and here you will be using coefficient b1 multiplied by a3 minus a1 multiplied by b2 divided by b1. Very similar to what you did when you evaluated coefficients b. So the same formula will apply for finding the coefficient c, and so on. So this is how you are going to evaluate all the coefficients corresponding to the rows that follows the first and second rows. And one thing important to note here is that this is similar to evaluating determinant, but it's not determinant, because in case of determinant you start from a0, you multiply a0 with a3 and subtract it from a1 multiplied by a2. But what you are doing here is you are doing a reverse process, while you're using a1 as the first element and multiplying this by a2 minus subtracting it from a0 multiplied by a3. So this is an important thing to note, because most of the students commit mistake in this part, and instead of using this formula they compute determinant, which is wrong. Now step 3 is after you populate all the array using coefficients of the previous two rows populated by using the characteristic equation. So after completely populating the Routh table, you will have to observe the number of sign changes that take place in the first column elements of Routh array, and the number of sign changes in the first column of the array gives the number of roots with positive real part of the polynomial. So what does this mean? So if you talk about this particular table, after populating this table, you will have to observe the first column of the table. You will have to look for the sign changes. For example, if a0 was, let's say, 5, a1 was 2, and you evaluated b1 as 3, c1 came out to be 1, and so on. So let's say you got 4 elements in the first column of the Routh table, and you observe that all these elements are positive and there is no sign change. And from step 3, if you observe that there is no sign change, then you don't have any root with positive real part. If you observe the sign changes to happen in the first column of the table, so it's written here, observe the number of sign changes in the first column's elements of Routh array. This gives the number of roots with positive real part of the polynomial. Positive real part of the polynomial means that the roots, those number of roots will be lying on right half of S plane and will be making the system unstable. Thus, if you have, for example, in this same case, suppose you wrote here as 5, 2, then you got here as minus 3, and then again plus 1. So you see that moving from this element to this, there is no sign change, while moving from this element to this, you have one sign change. Again, from moving from minus 3 to plus 1 will give you another sign change. So you have 2 sign changes. What does this mean? That this will give you the number of roots with positive real part of the polynomial. It means that if you have 2 sign changes, there are 2 number of roots with positive real part, and hence 2 roots out of 5, that depends upon n. So if n is going to be 5, then you'll be having in total 5 roots. So if out of n roots, if you have 2 roots lying on right half of S plane, they are enough to make the system unstable, and you will straightforward say that the system is unstable. So for a stable control system, there should be no sign changes in the first column of the Routh array. So this is important to conclude about the stability of any system, known as the sufficient condition. So after applying the two necessary conditions, you will be looking for the sign changes in the Routh table for that particular system, and that will give you the idea of the system, whether it is stable or not. Now let's try to do the first example. Determine whether this following characteristic equation represents a stable system using Routh Hurwitz criteria. So we look at this equation, we see that this particular equation satisfies the 2 necessary conditions, since it has all the coefficients with same sign, positive, and moreover there are no coefficients that are missing. Thus the two necessary conditions are satisfied, and now we move towards applying the sufficient condition, that is Routh Hurwitz criteria. And for this we'll be forming the Routh table given in this manner. So we start with s cube because 3 is the highest power that we observe in the equation. So we have on the left side of left column of this table as s cube, s square, s1 up till s0. And then we are going to use the coefficients which are associated with this equation, starting from 1 associated with s cube. So we have 1 placed here, then we have 4 which is placed here, then we have 8 placed here, 12 located here. And now we are going to use these coefficients to evaluate the coefficient b. And since we will be having only one coefficient, so it's not necessary to write this as b1. You can simply write it as b. So b1 will be evaluated using the same formula that we just studied. So you will be multiplying 4 with 8 and subtracting 1 into 12, then dividing it by 4. So this is how b1 is evaluated. So 4 multiplied by 8 minus 1 multiplied by 12 divided by 4 gives you the coefficient b1 as 5. Now what you are going to do is you're going to replace this b1 by the coefficient, the constant 5. The coefficient c1 will be evaluated in the similar manner using the coefficients corresponding to s to the power 2 and s to the power 1. So c1 is evaluated as 5 into 12. So you have 5 into 12 minus 4 into, since you don't have any element located at this particular location. So since no element is placed here, so you will be assuming this as 0. So this is an assumed 0. So you will be multiplying 5 by 12 minus 4 into 0 and dividing this by 5. Thus you get this c1 as 12, and you will be replacing c1 by the value 12. So this is the final required Routh table. And if you observe this particular table, what you see is in the first column of this table we don't have any sign change. So since you don't have any sign change in the first column of the table, and thus the system is concluded to be stable. So this system is stable. Since there are no sign changes in the first column, thus the roots of the characteristic equation have negative real part and the system is stable. And how many roots does it have? It has 3 roots, because you observe this from the characteristic equation which has the highest power as s cube. So this will be having 3 roots, and thus you will be having all the 3 roots with having negative real part, and thus the system is stable. Now the example 2 says to determine the stability of a system with transfer function given as c by r equal to this. So it is asked, apart from concluding the stability, it is asked how many roots it has with positive real part. So the characteristic equation is given by s to the power 5 plus 1.5 s to the power 4 plus 2s cube plus 4s square plus 5s plus 10. So using the same concept that we studied related to Routh Hurwitz criteria, we are going to populate this and see how the roots are going to behave. So starting with 1, so you have 1, 1.5, 2, 4, 5, 10. 1, 1.5, 2, 4, 5, 10. And then using these two rows to evaluate subsequent rows, you have 1.5 multiplied by 2 minus 4 into 1 divided by 1.5 gives you minus 0.66. So first thing that you conclude from here is the system is going to be unstable because there is a sign change already observed in the third row. But since if this question wouldn't have asked you about the roots with positive real part, so you, after computing or evaluating this particular value, it's not necessary to go further, and you can straightforward write that the system is unstable because there is already a sign change observed in the subsequent row. But since the question asks you about how many roots are there with positive real part, and thus you will have to form the complete table in order to determine how many sign changes are there, and thus how many roots will be there with positive real part. So if you populate this Routh table completely, we observe that there are how many sign changes? So if you move from 1 to 1.5, no sign change. From 1.5 to minus 0.66, one sign change. From minus to minus, no sign change. And again to minus, no sign change. then -2 plus 10, another sign change. So in total, in this particular case, you have two sign changes. And thus this system will be having two roots with positive real part. So if somehow using the computer program, if somebody asks you to locate all the 5 roots of this equation on the S-plane, so let's say we are required to compute all the roots of this equation and locate it on the S-plane. So what you might observe is that 3 roots will be lying on right half of the S-plane, while 2 roots will be lying somewhere on the right hand side of the S-plane, right half of the S-plane. And since we want to conclude only about stability of the system, irrespective of where the roots are located. So what Routh Hurwitz criteria gives you is the idea of stability of the system, whether the system is stable or not, but it doesn't gives you any idea of where the roots are located on S-plane. And since for determining the stability of the system, the information given by Routh Hurwitz is sufficient. So we don't go into a deeper detail of determining where the roots lie. But if you desire, if you like, you can using the simulation softwares or other softwares, you can compute all the roots and locate them on S-plane. So you will come to know that after locating all the 5 roots on the S-plane, you will know that you will see that 2 roots will be lying on right half of the S-plane, which is also proved by this table, the Routh table. So we answer this question as the system is a stable system and will be having roots with 2 sign changes, or roots that will be lying on right half of S-plane. Now here's the question so here's a task for you. The first, you can take, if you like, a snapshot of this question and post me the question or mail me the question. It's better if you mail the question.